Hello everyone, hope you are doing very good. So we continue our video lectures on chapter 4, which is the postulates of quantum mechanics. So today in lecture 17, let's discuss a little bit about the postulate number 1. So that's where we tried to finish last time. So the postulate number 1 basically says that any well-behaved function, means any well-behaved wave function, defines any quantum mechanical state. So quantum mechanical state means its information in terms of position and time, which is represented by its wave function. So let's take a quick look. You remember a free particle in a one-dimensional box, we define the boundaries at x is equal to 0 and x is equal to a. So according to the system's own condition is that the wave function should vanish at x is equal to 0 and x is equal to a. Okay, according to this. So you have seen it before. Now we already know that the particle in a box wave function is something constant multiplied by sine n pi x by a, where n is an integer 1, 2, 3, 4, etc. And we know that this is a solution, but before that, is it a well-behaved wave function? Should be a well-behaved wave function, but it's your job to test the properties that makes it a well-behaved wave function. So, but most importantly, the psi vanishes at x is equal to 0 and x is equal to a. All right. So my question is it the only wave function that can be written as a well-behaved function for free particle in a 1D box? Okay. So how about if I write psi is equal to x multiplied by a minus x? So that's what I wanted to talk about last time. So in a hurry, I could not write it properly. So now you check that the same function psi, it becomes 0 at x is equal to 0 and it becomes 0 at x is equal to a. So that means it fulfills all the necessary conditions for the particular system. That means for the particular confinement. Now it's your job to verify whether this wave function is finite, continuous and single valued, and its first derivative is finite, continuous and single valued. If it is so, then definitely this is another well-behaved function which is good enough to express the quantum mechanical state of a free particle confined in a box. So the point is, the postulate 1 says that any well-behaved function is good enough to define the state. That means it does not necessarily has to be an eigenfunction. So we know that this is an eigenfunction for the particle in 1D box, but this may not be the eigenfunction, but that doesn't stop this psi to become a well-behaved wave function to define this particular quantum mechanical state. Okay, so I hope you got that point. So we can do some numerical examples later using this psi value. All right, so we will try it out later. So now I guess this postulate number 1 is clear to us. Postulate number 2 we have already discussed, and also we have already discussed about postulate number 3. So now we are going to start the postulate number 4. All right, so let's clear this out and let's do it over. So before we begin to postulate number 4, let's once again very quickly revisit the summary of postulate number 3. So if you remember, what was said in postulate number 3 was that if A is an operator corresponding to an observable, okay, means a physically observable quantity, then if the operator A gets operated on its corresponding eigenfunction, then whatever the eigenvalue we get, that the eigenvalue becomes the observed value. All right, so life is pretty simple if there is an eigenfunction available for a particular operator. All right, so whatever you predict by the eigen equation is exactly the same you are going to observe, or you are exactly going to measure. So there is absolutely no problem with that. But now the question is simply that what if this A psi n not equal to A n psi n? All right, then what happens? So in other words, that what if for a system, whatever wave function that we get, if that wave function doesn't become eigenfunction of a particular operator, okay, so then what do we get? So the thing is, whatever the, in that case, whatever the physical quantity that we are going to measure, if we conduct a particular experiment and then whatever the outcome we get, all right, definitely that is not the eigenvalue, but whatever we get is exactly, that is something, a part of a statistical distribution. All right, and in that case we only talk about the average value or the expectation value. So here in that case we don't talk about any predicted eigenvalue. So let me write the statement whatever I told you quickly once again, so that it will be easier for you to follow and understand. So here we go. So I have written a statement to make it easier for you. So it says that if the system is not in a state as described by an eigenfunction, then one measures a distribution of values whose average is given by the postulate number 4. All right, so that means suppose if a state is already in eigen state, then suppose you are trying to measure its energy, then H psi is equal to E psi. So it doesn't matter whether you do a single experiment or a billion experiments, every time you will end up with measuring the particular value E, because you are going to operate H on psi and you are getting back the energy E. H psi is equal to E psi. All right, but suppose when that function is not an eigenfunction of another operator, suppose the momentum operator, for example. So if you operate the momentum operator with psi, you won't be predicting any values. Then what do? You go on to measure actually the same observable. But if you do a single experiment, you cannot measure anything and your outcome is erroneous. Then what you do 1 billion times, you perform the experiments 1 billion times, and whatever the outcome you get for everything, you represent that in a terms of distribution and you take the average value or expectation value. All right, so in that case the term or the statistical aspect, that is the average value or expectation value, it becomes important. So our postulate number 4 is all about that average value or expectation value, and I think we have covered that already at the beginning, at some part of chapter 3. That is, if I want to find an average value of the observable A or expectation value, it is represented as something like this. It is the general limit minus infinity to plus infinity psi star, and the corresponding operator we denote as A hat or A cap psi d tau. All right, now if the psi is normalized, all right, and also the psi is in eigenfunction of operator A, then definitely we can utilize this a psi is equal to a n psi. All right. So so here the psi can also be replaced by psi n, doesn't matter. Okay. So therefore, if both these two conditions are utilized, is normalized and eigenstate, then what we get is psi star psi d tau is 1 and the an part comes outside an. So what happens is the average value becomes the eigenvalue whenever this entire state is in eigenstate. But whenever this is not in eigenstate, then this gives you some value which is not according to the eigenvalue following this equation. All right, so this is all about postulate number 4. So postulate number 3 and postulate number 4 are very much connected with each other. So postulate number 3 says that if it is an eigenstate, the only value you measure is the eigenvalue, and postulate 4 says that if it is not in eigenstate, then you cannot measure a value or predict a value directly. So what we have to talk about is a distribution of values, and the average of which is given by this equation, and which we have already learned how, using this, how to calculate the average position, average momentum for a case of free particle confined in a one-dimensional box. All right. So this is all about postulate number 4. Now, quickly, we will move on to the next postulate, postulate number 5, which is the postulate related to the time-dependent situation. All right. So let's take a look at it. Okay, so the postulate 5 involves an equation which we are already familiar of. So it says the wave function of a system evolves in time according to the time dependent Schrodinger equation. All right, so that means, in other words, that a system, how does it change with time? Its time dependent behavior is dependent on the time dependent Schrodinger equation. So what was the time dependent Schrodinger equation? Once again, so I write in a little bit of shorter form. So H, the Hamiltonian operator, when operates on a wave function which is dependent on both x and time t, is equal to I H cross del psi del t. Remember, this x is also, the psi is also dependent on as a function of both x and time t. Okay, so this is basically the original time dependent Schrodinger equation, and we would not try to derive it because its derivation is beyond our capability, and we can guess, but we cannot state with certainty that how Schrodinger derived this equation. Anyway, as I told you again, I am telling you that this is one of the greatest gifts to the mankind. So this equation. So we would treat it almost like a Newton's gravitational law. So the thing is, of course, we can solve it easily. So how to solve it? So we solve by the separation of variable method, and in fact we have already solved this equation. So let's assume that this psi xt is a product of two independent function, which is the function of x multiplied by a function of time t. So if we, whatever this our assumption, we can now insert this into the original equation. So or we get h getting operated on psi x ft, all right, is equal to I h cross, then the psi x part would come outside, and then del t of ft. All right. So now we can try to solve it further, but the detailed steps have already been done in our previous lectures. So we can finally write the solution. Okay. So psi xt would take up in this form. So this is the special part, psi x, the variable separated part, multiplied by, we are going to write the time part, which is e to the power minus ie, all right, divided by h cross multiplied by t. So e to the power minus ie by h cross t. So now just take a look at this part, e to the power minus ih cross t. So this is almost, we can write that as if the time part is almost like a time dependent wave equation. All right, so we can write it as minus I omega t. So here the e by h cross part is almost equivalent to the angular velocity omega. All right, so this part e to the power minus I omega t, if we expand it further, we can expand it like cos omega something, some constant cos omega t minus I sine minus e to I sine omega t, etc. We can expand it. So the thing is, this part, it has a wave-like solution. Okay, so the time part, the temporal part of the solution psi xt has a wave-like nature, or has a wave-like characteristics, and the nature is also oscillatory with time. All right, so definitely what we see that the solution of a time dependent Schrodinger equation has a real wave-like character. So that's why the quantum mechanics once again is called the wave mechanics. Okay, so basically this is the postulate 5, and this is the outcome or the corollary of postulate 5. So it says that the solution of a time dependent equation has a wave-like character, or an oscillatory character. Okay, so now we are almost done here with postulate 5. So there are a few more points to be discussed regarding the last postulate. So let's clear the board and let's write it again. Okay, so few more important things that I want to talk about. That you remember the classical wave equation. All right, so it was like delta square u delta x square del to u del x square is equal to 1 over velocity square multiplied by del to u del t2, and you side by side you place the time dependent Schrodinger equation. Okay, so like h psi xt is equal to I h cross del psi del t. All right, so you see the time dependent Schrodinger equation contains the first derivative with respect to time. All right, so we can denote that as psi dot. This is the first derivative with respect to time, and here the classical wave equation is basically a second, means there is a second derivative, or we can call it the double derivative. That means this is u double dot. It is double derivative with respect to time. Okay, so there is a stark difference between even though we are talking about one dimension, there is a stark difference between the Schrodinger's time dependent equation versus the classical wave equation, which is also time dependent. And for a set of solution, means if I want to write a general solution for a time dependent system, so we can write it like this. All right, so psi n is equal to psi n x e to the power minus I e n divided by h cross t. And for a more general solution, we can even remember, we can apply the same principle for the classical wave, that we can take a collection of superpositions. All right, that means any combinations of the superpositions of these individual solutions. So we can write a more general solution, that is psi xt, then it would be basically any kind of superposition. So this Cn is some constant. All right, it would define that in which combination you are taking the superposition. So it goes like this. All right, and here n is equal to 1 to, all right, n is equal to whatever you can find. All right, n is equal to n. So this becomes a general solution, but remember this, in this case, so the total psi, this is not a stationary one, so this doesn't represent a stationary state because it is time dependent. The general solution, whatever we get, this is not, that means the superposition of those different solutions doesn't give you a stationary state. Okay, so that is a very important thing that we have to remember. So, and one more thing that I would emphasize, that now just think about the psi n xt. Now let's assume that if it is normalized, okay, or not, I mean the normalization is not required, even if we cross it out, the normality, if it is in eigenstate. All right, if it is in eigenstate, then what happens? You see that this integral psi n star xt psi n xt d tau, all right, is equal to, this becomes what? The complex conjugate of this multiplied by this function. So we have already done this exercise, that we have seen that this e to the power minus something t multiplied by e to the power plus the same thing t becomes e to the power plus and minus same thing means 0. E to the power 0 means unity. So this part, this complex part vanishes. Okay, so this integral therefore would simply be reduced to something like this. Okay, so that means what? That these two integrals we find where? Okay, so these two integrals we find, that means this is definitely, it is the probability density. All right, so the probability density becomes independent of time, that we have already seen it, and that is the explanation once again. Not only that, the average value, all right, because this part becomes very relevant when we talk about average value for a system which is already in eigenstate. So that means if psi n xt, whatever this time dependent psi is already an eigenfunction for a system, then what happens is psi, whenever you take the psi n the operator, whenever you take the operator sandwiched between these two, so for example, if you take this operator a here, and when a operates on this, all right, so immediately you get an eigenvalue a and an whatever, and then an comes outside. All right, so your average value as well as the probability density, this becomes time independent. All right, so remember, we can write that thing for average value only when this we can write ax a psi n xt is equal to a n psi n xt. That means the function is an eigenfunction. All right, otherwise, whether it doesn't matter whether your psi n is an eigenfunction of any other system or whatever, the probability density, no matter what, is always time independent. All right, and that makes our life simpler, because even for a time dependent system, its probability density doesn't depend on time. All right, so in chemistry we talk a lot about the probability density, because from this probability density the concept of orbital comes out, and the concept of orbital is not time dependent, so the shape of s or p or d orbital is timeless, so it remains constant. All right, so I hope that after all these postulates, means the 5 basic postulates, our understanding of quantum mechanics is little bit better. Okay, but we are not done here with the chapter 5 yet. Like there is one or at the most 2 more lectures to go, because we have to know a little bit more about uh, the quantum mechanical operator. Although that is not a basic postulate, but we can say that is one of the corollaries of our previously discussed postulate, which is postulate number 3. So one of the, in the next lecture we will learn one of the very special corollaries of the postulate number 3. Okay, so we will again see you in the next lecture. Till then, goodbye.